Hello guys, welcome to another episode of Xan Talk Show. So today we are going to continue the Advent of Code, Day 7. We started yesterday and we did for 2 hours, but we did not complete. Yesterday, the Advent of Code, Day 7, is a tough problem. And the problem is, so we're going to continue coding it in Wolfram language, okay? If you are here, comments and questions, post it, okay? And for those of you watching offline, post timestamp, I love to see your comments, okay? Be on topic. Okay, so yesterday the problem is basically construct a tree, Advent of Code, okay? You can see Advent of Code here, that's a website. They do this every year, about 24 problems, programming problems, TOEIC problems. So day 7, each problem, there are 2 parts. So day 7, they go by day, anyway, day 7, the problem is given this input, which is essentially the Unix command line prompt navigation directory. So you have the command cd ls, and your job is to, given this input as a string, you need to construct a tree that reflects the directory structure and the file size. And the actual question is to compute the sum of directories, find which one is what size. That's the actual question you have to answer. So you see, so here is the input, and you have to construct a tree. So yesterday we did a lot of analysis of the problem and decision about how to solve the problem, how to represent the tree. Eventually, so there's two representations of a tree. One is nested list, the other one is nested dictionary or key value pairs. We decided the key value pairs is easier. So we did the code. So let's start the code. Okay, so let's start the code. Let's start to code it. Okay, start Wolfram language. Okay, and let's go to yesterday so we can copy the code from yesterday. Okay, so here is the code. Okay, so let's okay, so copy it, close it, go to today's talk show and paste it here, remove that, pop it into its own buffer. Okay, so now let's start Wolfram language. We're gonna continue from yesterday. Wolfram language. Okay, start a new file, start the Wolfram engine, and let's magnify it so it's easier to see, and let's put it here. Okay, so I can easily get to it. Okay, so Wolfram language. So yesterday the code, here is extra input. So let's copy the code. Let's just run it. Copy it. So here's the code yesterday. Here's a huge input. And let's see. So we split the lines. The path is first of all we build a list of file path. Then from a list of file path we construct a tree. So we succeeded yesterday in building the list of file path. Okay, so we start with a global variable empty list. Then we start to add things to it. And here is the function that does the bulk of the work. This function, we map this function to the line part list. Line part list, each one is basically a line of the input, but separated into a list of strings. So that's a line parts list. So we map a function to all elements of that line, basically. And then in this process, we build the file path, X path. So okay, so now let's let's remove this one. This one is not needed. Okay, let's just eval the code. Where did it go? What? 150. Okay. I think we changed the font size. Okay, delete it. Delete the whole thing. Now we don't need this part. Copy the all, paste it here, run it. Okay, it's done. Now let's see XPath. So you can see that is a result we have. Let's show them in column form. Okay, so each of these sublists represent a file path, but each directory name is a element. So you can just join string, then it'll be a file path. Okay, and okay. So, but do we have a distinction between a directory or a file? Now, obviously, if the name is something dot something, that's a file. But is that always so? Let's check the input. So here's the input. Okay, so let's go look at the input. Talk show yesterday. Search for input. Okay, so here is the input. Copy all, new buffer, paste it, and let's delete all lines. Let's list all lines that begins with a $. Okay, let's do it again. Okay, so let's remove all those. Delete matching lines. That okay, done. Okay, so you can see some of them are the. Now let's list all lines that contains the word the space. Okay, so you can see all directory names do not have a dot in them. You can see, yeah, that's correct. Okay, that makes the problem easier. So directory names do not have any dot in it. Now let's delete all directory space. Okay, now all these are files. Now you can see, okay, so some files has dot something, but some files not. So some files has dot something, but some files not. Okay, so we have to. So this is ambiguous actually. So I mean our list is ambiguous. Hello, crazy frog. I have seen you before. So some of these file paths, we don't know it's a directory or it's a file. That's a problem. Let's see how do we solve the problem, because we are going to turn this into a nested dictionary, basically a tree. So to turn this list of file path into a tree, a nested dictionary, do we actually need to distinguish whether one is a directory or it's a file? Now we know that if it's a file, that's always the leaves of a tree. So, and if it's a directory, then it's not a leaf. Wait. Okay, some directory may also be a leaf node, because it just so happens there's no files in it. Okay, so let's write some notes. This is important to know. So let's go back to the talk show. That's yesterday. Go back to talk show today. No, that's yesterday. So today's talk show is this one. Some notes. Some file names contains a dot, but not all. Okay, that's important to know. The names never contains a dot. Okay, so that put that. So the name directory names never contains a dot. Okay, but some file names contains a dot, but not all. Okay, you know, we are asking this because we want to know, is it possible to determine it's a file or directory by purely just the file path? So the answer is no. Is it possible to determine a given full path is a or file from our X path? Okay, the answer seems no, because those reasons. Okay, so let's comment out this YouTube. Okay, the name never contains a dot, but some file names contains a dot, but not all. Okay, and we also discovered that files are all files. Any file is a leaf node, meaning they don't have children. But the may be a leaf node or a non-leaf node, because when the may have 0 children or no ls is performed on the. Okay, so that's some findings. Okay, so any file is a leaf node, but a may be a leaf node or a non-leaf node. Okay, so a directory may be a leaf node or maybe a non-leaf node. Okay, and again, we are trying to build a tree from this given file path. Now, is it necessary to know if a given full path is a file or directory? No, because it doesn't matter. This full path basically specifies the structure of the tree. It doesn't matter it's a file or directory. Okay, so that's important to know. So let's write it down. Okay, we are going to build a tree using nested dictionary from a list of full path, which is our X path. Okay, do we need to know if a path is the or file? Okay, answer no, because a full path, at least a full path, fully specifies the tree structure. Okay, so that's good to know. So one step further. Okay, so now we want to turn this into a nested dictionary. How do we do that? Okay, should not be difficult. Okay, we essentially this is how you do it in Wolfram language. So the tree is a association list we talked about yesterday. Let's go to Wolfram language. Okay, go to my website, you'll see a complete tutorial. And in Wolfram language, there are two major data structure. List is the primary one, just like any Lisp programming language. Everything is a list. Then, but there is a special data structure, and that is called association. Okay, so association is essentially, in Python it's called dictionary, in Perl and Ruby it's called hash table, in Java and JavaScript it's called a map object. It's basically a list of key value pairs, association in Wolfram language. And in Lisp it's called either hash table or association list. Okay, it's an old name, it's a variation name, association list, from which you have hash table. And in fact, the jargon dictionary is not from Python. The jargon dictionary is also very old. Probably the first one. So they are basically the same thing, a list of key value pairs. Okay, hash table, association list, dictionary, all the same, or map. It just so happens we have different names, unfortunate. So in Wolfram language, you use association, okay, key value pairs. So we use this to build a tree. The way you do that, close that. The way you do that is something like that, okay? So the tree is association we defined here. So, in the beginning, it's just an empty list of key value pairs. Then you can do it this way: the name 1, the name 2, the name 3, something equals to. So so this is what we're gonna do now. So the input, so this is a function, okay? So we want to map a function to this list of file path. And in the process, it should build this association tree, okay? So map, of course, obviously you map a function to X path, okay? And at level 1, by default it's level 1. Level 1 just means just like every other language is map. But in Wolfram language, you can specify a level. By default, it's 1. You can say 2, then you just map to like the children of the root, only those nodes. And you can say 3, that means the children of the root, only those, Or you can say -1, that means map the function to only the leaves of a nested list. Okay, so the map is super powerful, extremely powerful in Wolfram language. So this is worth mentioning because list is the primary data structure. In fact, the whole language, everything you see, every code is a list, just like Lisp. List is data, data is list. So in Wolfram language, you use list. Everything is a list. And you use nested list extensively. You may not see it here, but in fact, this is one giant nested list. Even the code or data, whatever, it's all nested list. So nested list is used everywhere. Okay, and then you have the concept when you want to map a function to a nested list, you can specify which level at what depth, or third depth to seventh depth. You can do that. One specific level or a range of level. In Unix you call it depth usually. just like when you do find some file name and dash depth, Anyway, so map is very, very powerful. So if you are programming, learning Wolfram language, you want to master this concept of level. Okay, I didn't say here because I'm trying to make beginner friendly, but you can see there's a level. You see, you can so a bit digression. So map, you can say, you see there's a level spec, and let's turn on JavaScript. You see, so this is kind of the standard syntax when you want to specify level. You can also say infinity. That means map through all levels, every node and every leaf of a tree. So this is extremely powerful. This feature, where you can map a function to any particular level or a range of level, is not found in any language I know of. You don't see them. You have to code it yourself, and it's not trivial. It's very not trivial. Because I did this in the 1998. I did a lot of this tree stuff. So if you're gonna write this function in Python, it's not trivial. Python, whatever, JavaScript, Haskell, whatever, even Lisp, they don't have these. Usually, you'll be not even a library. You'll be hard to find. Okay. So in most industrial languages, when you have a list, typically it's flat. You don't work with nested lists that much, unless you are doing linear algebra, computer graphics. Then at most you have like two-dimensional a matrix, basically a nested list where each element has the same length as every other. 2x2 matrix, 2x5 matrix, 3x7 matrix, that's all two-dimensional matrix, and all those are nested list. Okay, but in Wolfram language, you have that, but you can, each element may not have the same size as the other, so it's a tree. So, nested list represents a tree, and you can map to, you have this map function, map to any level. Okay. So now we want to map a function to the list of path, just level 1, and so the question is, how do you define this function? The function will basically do something like this. Okay, and we have to think about it. Now let's see the comment. I prefer watching people program than actually programming. Okay, that's interesting. So, are you joking? Sometimes you are joking, because what's the point then if you don't program, just watch? I guess that can be likened to watching sports. Right now the world soccer, football, is going on. A lot of other countries, South American, Italian, French, England, they are crazy about football. So, you're gonna have a riot. Yeah, so that's watching sports. Watching American football, or the non-round ball. American football, or rugby. Sports, baseball, basketball, NBA, and so on. So you have the sport of watching sport. So I suppose you can also have programming of the spectacle of watching other program. Is that fun? That would be new field, I think. That would be new. Haven't heard of it. How am I doing? So how many people? 2 or 3, I suppose. 2 or 3 watching me. Oh, 5. Okay. Say something. Okay, say hi. Okay, let's get back to you. Direct. How am my style? You tell me, and I'll go that way. Okay, I'm still live. I'm doing good. Voice check. Yeah. Okay, so right now our problem is to write this function. Okay, so but before we do that, it's prudent, it's a very good idea to try a toy program first. So let's do that, okay? So delete that, put this back in browser, and start a new Wolfram, and let's just do that. And let's maybe copy this list, okay? And paste it here, and color, syntax color it, move this out. So we're gonna work with this, example just for this part. Create a tree using nested dictionary out of a list of file path, okay? And we go back to browser. You can show it. So here is today's code so far, essentially from yesterday. Okay, but we're gonna work on this. Build a tree. Okay, so you begin with so first thing we want to make sure is that the list of file path is ordered by their length. That way we can make sure we don't encounter a deep knot before its parent. But I think from the input, they are already that way. Yeah, because you see, before you see a new directory, you do have the parent happening before it. So you have this directory, then you create children. Yeah, so we don't need to worry about the order. We can just map a function and go through them one by one. Okay, so here, this is the input. Let's say xx1, okay? Let's say x path list, okay? Now let's say, so this is the first, so up to here we build a directory. Let's shorten it even further. So let's try this. This is building one tree. Okay, so let's try that. Let's just use random. Okay, well, let's try something like that, simple. A very short tree. Okay, now we want to turn that into a tree. So let's just use x, okay? x1, okay? x2 equals to association, okay? Empty association. Okay, then we want to map a function to it. Okay, and how do we do it? So the first item is just let's see even shorter. So let's say even shorter. Wait. Oh, this list we got an extra bracket. Why is it extra? Let's try again. Okay, let's see what's x path. Why do we got the extra brackets? Let's copy it. Copy. Paste. Yeah, there's no extra. Must be copied error. Okay, so what you gonna do? Okay, so this part is wrong. and this part extra bracket, let's remove that. Let's fix this. Format them nicely, okay? Copy, replace that by that. Okay, that's not okay. So make them into one line and do this replacement. Okay, now it's much better. Yeah. Okay, so now x1 equals to, yeah, we can do that. Yeah, so we want to go up to here. Let's see. Okay, that's good. That is good. We just want to do this. X1 equals to, okay, so you need a bracket there. Okay, so here is a toy list of file path. We want to build a tree. Okay, so imagine the first item. So the first item when you, yeah, okay, so wait. So let's just manually fix this. Okay, so imagine you just got 2 file paths that, okay, so you don't even worry about this neither. Okay, so if you're gonna just have this 2 file path, what you're gonna do? So the first one, obviously, you want to do something like, so x2. Let's make it that way. So the tree, you're gonna have the names that. How are you gonna do? So association. So association. So the, yeah, so you're gonna add a key slash. You're gonna create that key, but what is the value? The value is gonna be another association, right? So let's think about how association correspond to the tree. I mean, a list of key value pairs nested correspond to a tree. So a tree, you have a root, and how do you represent that root? One way to do it is you have an association of a key, and that key is the name of the root. You know, in Unix tradition, that's a slash. You know, you can think of the slash as the name of the root directory. Even though it's not a directory, it's technically a file system mounting point. You know, that's Unix. Anyway, so you can think of as a directory. So the root directory name is a key. So this association have only one single key. That's a slash, okay? Then it has children, okay? But the children is of course association. But do we say null here, or do we say empty association? Like, which way do we go? I mean, for each step, do we say so when you have a directory, yeah, obviously. Yeah, okay, I know the answer. When you have a directory, it corresponds to a key in dictionary, and the value must be, of course, a list of children, so it may be empty. It shouldn't be null, because a directory means a folder. Folder means it's a container, so it's going to have children. So So it's appropriate to say, there's a new association, just empty. Okay. So yeah, so each time you encounter that, you do that. So let's say then we got into the second part. Let's make this way so it's clear. We have a list of 2 items. So then you get to the second part. So you start to have children in it, okay? Oh God! So maybe at this point you do need to know if a node is a file or not, because it's a file. You don't want its value to be association. Yeah, that's that's either way we can go actually, because in the end we can just determine those empty associations. Wait. So actually it would be better if we do know it's a directory or a file. Yeah, but to add that information, that means this list will not just be a list. This list will be a pair of lists. With the second part being telling you it's a dir or a file. And maybe perhaps you can also add a file size. Yeah, we can do that. But to do that means we have to modify yesterday's code. Okay, and yesterday we also have this lookup size table. Oh, okay, I know what to do. So lookup size table is basically all files. So lookup size table is again a dictionary of key value pairs. The key is a file path, okay? For example, that's a file path. The value is a file size. And all the keys in this size lookup table, they are all files. So in order to determine if a file path is a file or directory, we can just check the lookup table. If the key exists there, it's a file. Fantastic. Perfect design from yesterday. Real chat, hello. Nazrul. Secondary account, hello. Great. Yeah, nested map. Okay, so fantastic. We carefully, thanks to my methodological, analytical style of programming, we get the thing right the first time. So after 2 hours carefully thinking yesterday, this structure, this design, it's pretty good. I mean, that's the way I approach. There are other ways. There are better programmers. They do trial and error kind of exploration, and they can some of them can finish faster. That's good. But I usually take from I approach problem from a full logical analysis first. So anyway, the point is we got this size lookup table, very useful. Now let's go back to this, okay? So I guess first of all we need to check if the full path is a file or dir. Okay, by checking the what is the size lookup table? Yeah. then it equals to if is the. So if it's a directory, then the value is association empty, meaning a folder, a container. If it's a file, oh, we're starting to build a tree. Fantastic. This is gonna be one-shot operation. One shot, run it, and it works, and it will be correct. So if it's a file, yeah, so first of all, you need to check the lookup table. So let's look at the lookup table. Okay, so let's define a variable, current path. Okay, current path. Current path is, that or that. So current path. So now if you want to see that current path exists in the size lookup table. Okay, so how do you do that? We go back to Wolfram language. We go back to association, advanced pattern matching function association. Okay, then you go to check existence. Okay, key exist. There it is. So you say key exists, and the association is a size lookup table, and the key is the current path. Okay, is file, another temp variable. So is file equals to that. Okay, is file Q. Q in Wolfram language, by Wolfram language convention, Q means a question, which means a predicate, which means anything ending in capital Q always return true or false, nothing else, either true or false, always. So this is similar to the predicate in Lisp, where they usually ends in P, like file exists P, number P, is it a number P, that's a Lisp convention ending in P. In Wolfram language, ends in capital Q. In Ruby and in Scheme Lisp, they ends in a question mark. This is very nice to know. Let me show you. Okay, let's go digression. So I have an article on that. I talked about that before. Predicate. Yeah, I don't have it here, so you have to go search. Xali search. Predic. Okay, predicate in programming language naming. Okay, so in Lisp you have bound P, buffer modified P, F bound P, feature P, file directory P. They return true or false. That's a Lisp convention. In Scheme, it's question mark. Scheme, Lisp, closure Lisp, and the Ruby question mark. Okay, in Wolfram language, it's capital Q. Q stands for question. Now this is interesting. The naming of things. So which one is better? Why doesn't Wolfram language follow the conventional computer science and use P? P for predicate. Well, because predicate is kind of a esoteric jargon. It came from logic. It came from the field of math, logic. Predicate. In logic, the meaning is slightly different in computer programming languages. In logic, a predicate is a assertion. Something is true. All people are good. Okay, that's not a question like programming languages. When you have a predicate, it just it's an assertion. It's a statement. Okay, it's an assertion. But in programming languages, you don't have that in general, unless you are talking about logic programming languages, a very niche specialized language. But in all other languages, C, C++, Java, Python, Ruby, whatever, when you have a predicate, that just means the function returns true or false. Okay, so predicate is a jargon originally from logic. So, but programming is kind of came from math, in the early days. There's no programming, then started. So you borrowed a lot of jargons from math. So you have predicate in Lisp, meaning a function returning true or false. And you have a convention, it just ends in P. But Lisp got a problem though. Like some function ends in P, but it's not a predicate. So it's not very well. The naming of this Lisp convention is not very well done in Common Lisp, in Emacs Lisp. Because some functions ends in P, but it's not a predicate. Okay? For example, there is forward sexp. There is pop. Let's magnify. There is pop, there's different group, there's make sparse key map, they all end in P, but it's not a predicate, obviously. While the others, list P, number P, string P, symbol P, vector P, 0P, they are predicate, meaning that they always return true or false. And there's inconsistency in Emacs Lisp. For example, some is dash P, some is just P. So, it's a problem. You can look into these different aspects. These are things that I find, many times in my study of programming languages, you find these kind of things, but you never ever seen the industrial programmers talk about these issues. Like never, not once in my 20 years reading /dot, Hacker News, Reddit, or whatever, online, the hackers, the Python forum, Python mailing list, the Emacs list, Emacs dev mailing list. These issues, they never thought of, it's like kind of strange. They never talk about this. But the designer programming language, they have to. Because why is scheme Lisp, closure Lisp? They have a convention of using a question mark. And it's absolute. If a function ends in question mark, that always means the function returns either true or false. Okay, this is good. This is good. Who came with, who did it? Well, whoever created scheme and closure Lisp, for example, closure Lisp, the guy, what's his name? Rich Hickey. It doesn't come out of nowhere. You have to design it. You have to implement closure. So they know these people. They thought about. They have thought about things. Okay, scheme Lisp, closure Lisp, question mark, which is excellent. Okay. Now, but what about Wolfram language? Why is it Q? Why don't you just use P? Just like, be a good boy, follow the convention, P predicate. Well, the issue is predicate. What the fuck is a predicate? Do you know? Nobody knows, unless you are a logician or mathematician. So the predicate is not intuitive, the naming of things, okay? Intuitiveness is one of the good quality in the naming of things. So the Wolfram language, Stefan Wolfram, he went with Q. Q means question, so everyone understand. You don't need a math degree, that is why. Question is also good, question mark is also good, but in Wolfram language, question mark is used for, because it's used for other syntax, so you don't have, question mark is not allowed. What is question mark? Yeah, question mark is a shortcut for help, anyway, so it's not allowed in identifiers. That is why Wolfram language use Q, and Ruby uses question mark, okay? Now, Ruby is actually, Ruby came from Lisp and Perl. Ruby, you can say Ruby is a synthesis of Lisp and Perl. So you can see a lot of Ruby programming language, their structure convention is kind of a little bit similar to Lisp. So anyway, that's a digression about predicate. Okay, naming a predicate. Okay, let's go back. Okay, I want to copy this and put this into talk show. So let's just put it somewhere since it's something we talked about. Okay, now back to the code. Okay, so back to the code. So is file Q, okay, is file Q. So if it's a file, then you do something, otherwise you do association. Okay, so what if it's a file? Okay, so when it's a file, you want to assign it just the size. Okay, yeah, let's do. Okay, let's do this. Let's see. So this will return. Wait, let's see. How do you access a dictionary association? Okay, so that's how you check if it exists. But there is also get value. Okay, so look up association key, but if the key do not exist, it returns missing. Okay, for simplicity, let's forget about efficiency. Let's just have clear code so people can understand, because most people are new to Wolfram language. So let's go with more code. Okay, so is file that, and if and file size. Okay, let's just say file size. File size, you look up association and key. Okay, association and key. Okay, so if it's a file, you just add this file size. Yeah, let's just do this multiple variables. Okay, yeah. So the tree something something current path. Okay, the tree current path. Wait. Okay, so this is assuming that the current path is one single element. Usually it's not. Okay. So now let's say current path. Let's pick one example. Okay. Yeah. Let's say that. Yeah. Okay, what you gonna do there? So current path is that. Then what you gonna do? You want to do something like that. Okay, that's probably what you want to do. So the first part gives you the first part gives you a association, the container for that. Then the second part, which is okay, we're getting closer though. Second part, if it's a file, so if it's a file, then just put the file size. Otherwise, it's a directory. Put in association. Okay, yeah. Okay, that also So these are two scenarios of our code. Does that work? I mean, what if we have, let's say, something like that. So given a full path, you construct this, then sets its value. So Herba says you are going to have a null pointer error. Why? I'm not seeing a null pointer error, okay? So anyway, so here is the, yeah. Okay, let's start to build it. Now, before we build it, essentially we want to put this section into this function. Before we build it, now notice the list of path. A given full path is actually a list of things. So for each of the element, you want to make it into this key syntax. So one way to do that is to build this sequence of symbols. Then you call eval. Just like other languages eval. That turns that into an expression and evaluate it. That's one way, but that's usually not efficient because in just about any programming language, you want to avoid calling eval as much as possible. Especially in industrial languages such as C, C++. I mean, C doesn't even have it. But in Python, in JavaScript, you can do eval. And in Lisp, Emacs Lisp too. But usually you don't want to do that because you have, first of all, you have security issues, but mostly it's slow, okay? It's kind of meta-programming. It's meta-programming. Meta-programming is very powerful, but you want to avoid meta-programming as much as possible, okay? Most Lisp beginners don't know about that. They think meta-programming is, dramatic. They always use that, like Lisp macros. No, you don't want to do that. You want to avoid meta-programming as much as possible unless you absolutely, there's no other way, then you do meta-programming, okay? Okay, so back to the problem. So now, we want to build this syntax. Is there a way without having to require you to use eval? Yes, I think so. How do you do that? Yeah, let me show you, okay? So you are given a list of things. Let's say you are given A, B, C, a list. You want to turn that into that, right? You want to turn that equal, let's ignore that. You want to turn that into that. But what you can do is you can nest, okay? You want to, this is a short syntax. What is a full syntax? Let me see. So association, add a key. Okay, so this is one way to do it. Add a new key value pair. This syntax is traditional. I mean, like in other languages, Perl, JavaScript, Python, you also do it similar to that. But that's not a functional. There's a problem with that using operator. This is, you can think of that as a operator form. And when you do a lot of functional programming, you do not want to use operators. You want to use the functional form. Always use the functional form. Why? Because when you use functional form, you can manipulate, you can use the full power of functional programming to manipulate the function, to take the function as input to another function or output a function, and you can manipulate the pass whatever argument you want. But if you have a operator form, you cannot do that. You have to just in Python, in JavaScript, you have to build a string of that, then eval that string. No good. Okay, so that is why you want the functional form. This is one great tip about functional programming. I mean, it's a tip you'll get to know if you do a lot of functional programming. So you want to use this instead of the assignment operation. But in Wolfram language, actually, they are equal. They are equivalent. This actually, the compiler will turn this form into that form. Oh yeah, that's right. So actually, we can do it something like that. Yeah. Fantastic. But anyway, I was going to show you using nest. Okay, but okay, let's get on to get the result. Let's get to work. Okay, God, this is already 1 hour. Ah, shit. Anyway, that's Ksa Talk Show. Ah, God. So we can do it this way or we can do it this way. But how do you do it this way? So let me show you, okay? So associate variable key value, okay, right? That's how you do it. Okay, so the second argument associate to. Okay, so you use associate to. Right. So let's write it out clearly. So that is equivalent to, yeah, that is equivalent to that. How do you know? You can do this. Let me show you, okay? So you can do this. Let me show you, okay? Because this is interesting. Wolfram language. You see? Let me show you the other way. So you see, wait. That's not the full form. Okay, yeah, we don't want to use this. But why is it not? Let's look up the documentation, okay? This is a function. Let's, so association, you can add a new key value pair by associate to. Now let's go back to association. Let's see how they explain. Oh yeah, okay. There's some tricky thing going on. Okay, anyway, we want to use this form, okay? But how do you nest it? Okay, how do you get, okay, you have to do association. How do you get a value? Let's see. let's use the function form. Okay, so you can do association key, lookup key, look up a key A, then look up B. Okay, let's do this. Look up C. That's how you nest it, okay? Yeah, look up CBA, okay? You nest it 3 times. Then the result is a association, which is AB, okay. Wait, so you look up A, then you look up B. Yeah, should be in this order. Then the last one is special, okay? Hold on a second. So you nest them like that. This will be equivalent to that, okay? That and that should be equivalent. But if you want to assign, let's do it again, okay? If you want to assign, let's say, sum, then what you do is that then what you have to do is that okay, you look up A and look up B, then you want to associate 2. God, you cannot use associate 2, can you? Because associate 2 requires a variable. Fuck. So I'm thinking well, you can just say that that's not good. Okay, we have to dive into association a lot. Shit, it's 80 minutes. How do you we need to build a tree, a nested dictionary from a list of file path. And right now we are taking apart the file path component, and basically we want to write this function, map a function to a list of file path. And this function will essentially do things like that. Each line is one example. But right now we want to turn this code into kind of a function. So the function input will be a list of directory names or file names, a list of directories and file names. And you want to turn it into something like that. So why can't you just if you use eval, that will be the easiest. So actually, association in Wolfram language is actually a function. Yeah, because that's a esoteric detail. I'm not too familiar with yet. Association is a new thing about 8 years ago in Wolfram language. So anyway, so why don't we just write this directly? It's so simple. Yeah, so okay, so you want to map a list of names, string, turn them into that. So you want to write a function you want to turn a function into given a list of values into that. Head. So this would not, so how do you do that? Should not be too difficult. So let me think. So you got a list of items, let's say ABC. You want to turn that into that. Okay, the easiest way is to use nest, actually, just like we are trying to say here. Yeah, so let's go here. So the easiest way is actually just use nest. Let's see. Nest something length of the list, okay? Okay. And yeah, let's see, for example 3, then let me show you how it works. Okay, so let's try the tree. Is that okay? That's empty, but let's say dr. Okay, the tree that okay, what's its nest? What's the syntax? Expression n. Okay, so you have to, oh, you cannot use nest, you have to use fold. Yeah, because for each time you need to take an argument ABC. Hey, Ring Tingle, thank you. So you cannot use nest, you can use fold. Do you guys understand? Like, are you guys making sense what I'm doing? You know, I'm guessing Wolfram language is new to you guys, so am I actually making any sense at all? So anyway, fold. So fold, for example, let's see fold. Okay, fold is like Python's reduce. Okay. So f, x, and list, okay? Again, fold is like Python's reduce, okay? So you can see, okay? But so let's do that here. So the list is gonna be ABC, for example, directory names or file names. So you're gonna fold it into that. Okay, you don't need the 3. Okay, so let me show you how this works. What? It's not folding. What? Oh, f needs to have 2 arguments. Wait, something is wrong here. Oh yeah, you forgot the comma. Okay, of course in Wolfram language, item needs to be separated by comma. Okay, there it is. You see, so So each time it takes 2 arguments, but you don't want it to fold it that way. You want to create this structure, okay, not that. But using fold is a key, okay, but we have to think about how to do it. Okay, so I'm getting tired. Yeah, don't forget the comma. Okay, so fold AB, it takes 2 arguments at a time, and you want it to return, for example, fold AB, you want it to return that. Yeah, so okay, so you want the function here. Let's write down the function, okay? Let's make that a function. And here is what you want. First argument, second argument, okay? Let's try this. Okay, let's check. Yeah, that's one thing. Do it. Close. Okay, now let's close. We're getting there. Okay, let's see A, B, C, D. Okay, something's still wrong. We don't want it to go inside at all. But this is getting close. You know, let's do this so you can see. Now we can use range at 10. You see? There is a nesting going on, but not the way we want it. You see? F2, there's F3, F4, you know, some kind of, we want to sequentially go to the front. Okay, let's think about this. So each time you just kind of append a thing to the end. Each time you want to append a thing to the end. A, B, C, yeah, each time you append a thing to the end. So when it begins, you know, it begins with 2 arguments, but you want it to not begin with 2 arguments. Each time you take a list of things, I got a better idea. So we are doing this all wrong. Let's hope it doesn't crash when I do this, okay? So fold. Some examples. Each time Okay, I got it. Wait, fold must take one argument or two. Fold takes two arguments. The function, the function to the fold takes two arguments. The function for folding takes two arguments. So we don't want to use fold. Wait. God. Why can't we use nest? Well, because we need a list of input. Okay, let's read a bit. Let's read about sequence fold. Sequence fold, okay. Sequence fold is new 2015. Okay. Sequence fold. Sequence A, sequence B, A2, sequence A3. Okay. Fold list, fold pair list, nest list. Functional iteration. Fold sequence fold pair. What is fold pair? Fold pair is also new 2015. Okay, fold pair. Let's see what's fold pair list. Gives the list of successive xy and xi obtained by applying f to pairs of the form. What? Okay, let's go back to functional iteration. Nest list, nest graph, fold list, sequence fold while. Fixed point, nest while. You know, all these are basically loops in a functional programming style. Okay. Okay. So the function takes a list. We want to turn that into that. Okay. Does anyone know? This is a very, very interesting problem and pure Wolfram language term rewriting problem. But I have to think about this though. So you are given a list. You want to go through them by a loop or by a map or by nesting or by recursion, however you do it. Given a list, you want to basically turn it into this expression. And this expression in Wolfram language is actually nesting. You nest a function in front, so this expression in Wolfram language is actually like this. Okay, let me show you. Okay, so you consider that as like that. Okay. Okay, this is how it actually is. I don't know if you can, so basically this part is one function. Then this function function name is actually that part, and this function, the function name is that. So it's actually nesting in front. That, that's what that means. So okay, so we can, so let's, oh, I got it. Shit, good, I got it. So now, so what we do is that we nest in front, okay? Remember, nest in front. So for each time, so you want to put this dollar sign, I mean the thing, wait, why is that not correct? How is that? Let's see, what's the precedence? That's right, so the problem is, can't we do it? Okay, so something like that. Well, the problem is, very pure mathematical problem here. You don't need to know Wolfram language. Anyone, you can try to come up with a solution. You are given a list. You want to turn that list into that. So the first one is the tree A. So you map a function subsequently to the list. So you want some kind of nest or fold. Now you cannot use nest, because if you use nest, each time nest doesn't take a list of arguments, because in this case each time you need a different argument A, B, C, and you want the function to take one argument at a time. So you want the function to take one argument at a time. But for fold, the function return, must take two arguments at a time. Wait, what's going on? So you see, this XABC, you want to somehow avoid that X. You want to avoid this, remove that X. Wait, but all these are a function of two arguments. You see, this is one argument, then B. Then, so it always, the function to fold always takes two arguments. Okay? The function to fold always takes two arguments. So So you have a case of, for example, function, and given the arguments a and b, then you have, let's say you did this, then you have a, b, then you are given an argument of, well, first of all, you have the argument of a and b. Then suppose you get that. Let's suppose, okay? Then you have that and c, okay? And what you want is, let's make this, let's put it here. Okay, AB becomes that, that's right. Then you have the argument like that. Okay, let's put comma, okay? So that should become that. Okay, so that should become that, okay? So yeah, okay, so now it's clear. So you begin with F. You begin with F, and each time you get an argument, you just append it. Yeah, so it's so obvious, But then why? But how do you? Why is fold? So you basically you want it to be a single argument. So the second argument you don't care. Okay, this if you don't care about the second argument, no, you cannot do. Well, if you don't care about second argument, then you get FA. Let's see, maybe that's all we have to do. I don't think so. Not here. What? Yeah, if you don't care about second argument, that's what you get. So what if you say 2? Okay, so the problem here is somehow you need to turn these 2 arguments into 1. Wait, why is it not work? So it's very, very simple. Each time you take an argument, suppose your function only take 1 argument. So each one you take an argument, you just append it. Right? So FA is that, then you get, you basically nest it. So you want the recursion. You want the nest. You want the you want the nest. Okay, you want to call that. But however, nest does not take it does not take any list of arguments. Okay, so okay, I know what to do now. Nest while. Okay, nest while is also new. Oh, nest while is in 1999. Okay, that's not so new. Okay, nest while is what we want. Okay. No, not nest while. Actually, the thing we want is just fold. Okay. Yeah, the thing we really want is just fold, but we have some logical problems. Okay, so let's think. We have logical problems of trying to resolve fold. Let's write them out. So people looking at watching me staring at the screen can understand the problem we are trying to solve. So what we really need is fold, but we need to resolve the logical kind of the paradox. So fold allows you to take a list. Okay, let's think about this. So fold takes a function. The function always takes two arguments. Why? Well, the essence of fold is that it allows the function to take a list of things and apply it recursively, each time taking one element of the list, okay? So fold, you apply, when you do fold, when you do fold, you can have these forms, but essentially you take a list and it returns that. Okay, so function a x, so it takes two arguments. So it essentially nests. Do we have a fold right? No, you don't have a fold right, okay? When you take a thing and it nests it, so why is this? God, this ABC is no good. You don't want it to nest. That's the problem. You don't want it to nest. Oh, I think I got it. There it is, a function without head. Okay, without head is syntax error. You have to have some kind of head. Yeah. Okay, so what about these? We bracket them in a different way. Syntax error, yeah, but wait, actually that oh yeah, so you can't really do that. Yeah. Okay, I don't know. I cannot resolve the logical issue of fold. It needs, I need some kind of understanding. I mean, the issue is this. Fold essentially allows you to take a list of things. So fold is like a nest. Basically, you apply a function to its own result recursively. But except fold allows you, except that you want to, for each time it calls itself, you want to take a value from a list. So fold is a kind of recursion or nesting of a function, but for each time you take a new value. Okay, so the confusing, I mean, the thing I'm trying to resolve is that, so in a sense, fold should take one, the function for fold should take one argument, only one argument. But why is it takes two? Okay, so you take two arguments, you get a result. Oh, okay, so when you get the result, that's right. So it's what I want, what we want is a result applied to the new thing, not repeated. Yeah. So we actually don't want to repeatedly or recursively apply a function f. You know, in the case of fold, the function f is repeatedly applied each time. So you always call f. Okay? And every time it takes two arguments. The first argument is whatever is a result. Okay, and the second argument is a new item from the list. However, you are still calling f, you know, and feed those arguments. So you do that, you get a result, then you call f again and put the new result into the argument and another part from the list. You do that again you call f. So you call f many times. That's fold. You are essentially doing a recursion or nesting of the function f. The main point is that f is repeatedly called. Okay, that's fold. Now in our case, what we want here, we do not want to call a function repeatedly. There's no one single function that are called repeatedly. Instead, we want to start with the tree function. Then when we get the first value a, you know, it becomes that. Then when we get the second value b, we don't want to call f or the tree again. We want to call the last result as the function. Okay, so now we'll get the result is that. Okay, this is the result. Then we get the new value c, then we just apply the result to the argument c. Okay, so each time you take the previous result as the new function to apply to the next value in the list. Okay, now remember that is a key. That is a key. That is the logical essence what we are doing here. You begin with a function called the tree and apply it to an argument. Okay, you begin with a function, take an argument from the list, apply it, you get a result. Now use this result as your new function. Take another argument from the list, apply it, then you get a new result. Then use that result as your function. Okay, so what you want is some type of it's also recursion. Okay, but it's not a recursion of a fixed point. It's not a recursion of a fixed function. Rather, so yeah. So this is not a recursion. So what's going on here? So each time you get a result, then use that result as a function. So you have some kind of functional level programming, okay? Right, you don't have like, you have some sort of so-called functional level programming. Now I wonder, the Haskell people might know a few things about this. I'm not sure, I'm not sure about the Haskell people. But anyway, so start with a function. Apply to a argument, you get a result. Then this is interesting. So why is there this is a new kind of yeah, and even in normal recursion in other programming languages, such as Clojure, in scheme list, when you do recursion, you call a function, you define a function, and in the function body, you call the function itself. So that's recursion in other languages. But in that case, you are still calling a fixed function. You repeatedly call it. So it's, but in here, what we want is not, there's no fixed function. So this is not a, so you would say this is not a recursion. This is just a loop then. Yeah, so if you use a procedural language, then this is essentially like assigned to a variable in a loop. You do something, you assign the result to that value, and you do something again, then you assign the new result to that value again. Kind of combine the previous thing. Okay, so, but how do you do this? How do you actually code it? So you want to, so the result, so you apply a function to an argument, get a thing, get a result, then have the result apply. Okay, this is 2 hours, and we haven't resolved this. I think maybe I should stop. Who is watching? 2 people. God, this day 7. Today's problem, day 7. We still have not solved it. Although we are making steady steps, I don't think I'm stuck anywhere, because I'm not really stuck. I might be, it may appear that I'm stuck this, but I don't think so. This is a clear problem, and I am 100% I can work it out. It just needs some time to think about this, and I want to do it in a proper way. I'm trying to build this in a correct, in a good way. I don't want to, I can try to use eval. Maybe that'll be simpler, and there's quite a lot other ways to solve this that I haven't tried to think about yet. you know, but I'm just like, you know, hitting a wall, and I want to break through that wall, and I know I can. That, you know, I'm just stuck with this idea. So I was trying to resolve, you know, what is the, you know, logical, you know, what's the difference between nest and fold? What's their implication, and what's their relation to the number of arguments, the arity of a function, things like that. So, and right now we found that we want the thing we want is apply a function to a value, get a result, and this result is supposed to be a function. Then you apply this function to another value in a list, you get a result, and that result is again a function. Okay, so is this, I can tell you now that this is not that frequently done in Wolfram language, because when you have a nested head, that doesn't happen that often. Okay, let's say it does happen, but let's say 30% of, you know, Wolfram code, you know, functional, basically you have a functional function returning function. But why is this? I mean, is there a built-in construct, like I need to figure out where does this fit into the Wolfram language, you know, iteration kind of functions. You see, there's a tech node. There's you know, these tech nodes are originally written by, they are originally from the Wolfram Mathematica book, which is over 1,000 pages, and they have added new things. So in this section, so, you know, originally it came from Wolfram, it's called Mathematica book, over 1,000 pages. So, but if you look at them, you know, I read them cover to cover 3 times in 1990s, but today you might have some new things not printed. The Wolfram, the Mathematica book stopped printing in 2004. So anyway, so here you have function operations, and you have, so I want to see where, you know, what we are trying to do today, where does it fit in this? We can do that, you know. Yeah, I can actually get it to work. You know, we could actually, what we can do is just use nest and write a function such that the function contains this list of items. So each time it calls itself, it takes one of them, reduce, you know, it remove one item until there's no more item. When there's no more item, the function returns itself. Then you get the result. Yeah, we can do that. Okay. Okay, but okay, for now, I think what we are going to do is we're going to take a break, and let's see. Maybe after the break, then that's it for today. Maybe after break, I feel like coding it, then let's continue, because right now it's already 2 hours. Okay, yeah, I know all these functions. Okay, sequence is okay. Okay, so be right back, 5 minutes. Okay. Hey, Kassan, Harold. So I'm gonna take a break. Be right back, 5 minutes, and maybe that's it for today. You know, we stuck with this problem. Okay. So let's highlight it so other people can see. Okay. Gonna turn my video off. China cheapo. I'm back. Okay, we might do another break. Let's see, 2 people. Is that right? 2 people, okay. Okay, let's try something. Let's try. So we don't want to fold. We want a nest. Okay, so let me just write it. We want a function that calls itself. We want to nest a function. So when you do nest, when you use nest, you are also, when you do a nest, you are also recursively calling a fixed function. You are calling the function, it returns something, then you see, then it calls itself again on the result. So you want to do nest, okay? Yeah. Okay. Nest a function. Start with nothing. Okay, so you need to start with something, but we don't want to start with something, and we don't want a fixed number of times. The number of times we repeatedly call the function depends on the length of the list. So we don't want to use nest. What we want to use is fixed point. Okay, fixed point we'll call f on an expression repeatedly until the result no longer changes. Okay, so f apply an expression then it returns something. Let's see, fixed point, and let's try it. Let's say 4, okay? Yeah, normally it just it just call the function itself 4 times. Fine, next, call f again, call f again, call f again. So f given an argument, it returns something. Then you call f again. You see, that's a problem. We don't want a fixed function. We don't want to. We want the result to be a function. Yeah, this is interesting issue. This is an interesting issue. We don't want to repeatedly call a function. Instead, we want to repeatedly have the result becomes a function. Okay. So that is the main problem we have. And what is this thing we want? Is there a name in mathematics, in functional programming, where you start with the list, each time you apply the function, then the result, you want to use the result as a function, then apply to the next thing. Is there a name for this thing we are doing? Harold, hey Harold, where are you from? Anyone knows? I guess nobody. Replace repeated. Okay, let's see, replace repeated. No, that's not. Okay, so we can pattern. Yes, we can use pattern. So we want to turn this pattern into that pattern. Pattern matching. Okay, let's try to sketch out the idea. How do you do that? Okay, let's sketch out this idea. So if we use replace repeated, so we begin with that, and we begin with the list. Then we want to replace repeated, and the pattern is gonna be a rest. Okay, you can say rest. Okay, becomes a F whatever. Nah, wait. Yeah, we want something like this. Okay, becomes not sure if that will work. Let's see, let's hope no recursion limit reached. Okay, yeah, it says it cannot be combined. Right, so when you have that, oh, okay, wait, you got the arrow here. Yeah, that's just ABC. One or more becomes A, and rest. Okay, no, something like that. Okay, it doesn't apply because you need F here. Okay, something like that. Let's do it here this way. Okay, so instead of A, B, C, let's just use 1, 2, 3. Okay, let's say that. Okay, and okay, that's, I think that might work. Fantastic! That is the solution. Fantastic. Now, for the last one, we need to do something about it. Okay, this is fantastic. This is the way to go. This is pattern matching. Okay, this is transformation of expression. Now, yeah, again, this is interesting because we want this some sort of recursion or loop where you apply a function to a list of things. First, you take the first element, you apply a function to it, you got a result, then you want to apply the result as a function to the second element. You got a new result. Then apply the result of that to the third element. You do that repeatedly until, okay, so until there's no more element in the list. Okay, so we can do it this way. Fantastic. That is what we want. Okay, so yeah, but the last part you want to so essentially this is what we want to do. Yes, this is what we want. Okay, and right. So what is this pattern? I mean, how do you call this in functional programming paradigm or logic? Is there a name? Is there a name for this kind of loop or recursion? So is this a recursion? Recursion, yes, this is a sense of recursion, but it's not nesting. It's not the typical recursion using a fixed function. Well, it can be. I think it can be. So in any case, I think this is a recursion. This is a recursion because the function apply an argument, it returns something, okay? And you apply, can we turn this something into the function itself? So you need a function such that it takes something, returns a result, and if the argument you want it to return a result such that the function does not appear in the result. So this is not. So the question now is can we call this recursion? This part, is that a recursion or not? In some sense it is. It's a loop. But in some broader sense it is a recursion. Okay, in some broader sense. Or maybe it's not. I don't know. This is actually interesting because you are not calling a fixed function repeatedly. But that might be a narrow definition of recursion. So what does Wikipedia say? Let's look. So recursion, so recursion, there is lots of, what they talking about? So they are talking about the general concept of recursion. You have recursive humor. That's idiotic. So here in mathematics, recursively defined sets. Recursive definition. Example, the natural numbers. Okay, and you have proof procedure. Another interesting example is the set of all provable propositions in an axiomatic system that are defined in terms of a proof procedure, which is inductively or recursively defined as follows. Okay, finite subdivision rules. Okay, functional recursion. A function may be recursively defined in terms of itself. So function is recursively defined. Yeah, you define the function involving calling itself, okay? A famous recursive function is the Ackermann function, okay? Which, unlike the Fibonacci sequence, cannot be expressed without recursion, okay? Proof involves recursive definitions, okay? Recursive optimization, okay? The recursion theorem. In set theory, this is a theorem guaranteeing that recursively defined functions exist. Given a set X, an element A of X, and a function fx to X, the theorem states that there is a unique function f natural number to X where n denotes a set natural numbers such that f0 equals to A and what the fuck, for any natural number n. The recursion theorem. Okay, so then you have the computer science recursion. A common method of simplification is to divide a problem into subproblems of the same type. Blah, blah, blah. So we have here now the typical programming language except recursion, okay? So today we run into a kind of an issue about nesting and recursion. What do they really mean? So this is when we need a exact formal definition, because the thing we are trying to do, turn a list into that. This is kind of strange. This is new to me. Is it new to me? Is that a recursion or is that just a something? Can you call that a recursion? So you are defining. So if you want to, how do we formally state the problem? We want a function that take a list and return a somewhat a nested function call. So is this, how do you call this function? Or how do you, or is this just, or how do you, if you define this procedure, is there a name for this, well, first of all, it is certainly a recursion because this procedure repeats itself unchanged. This procedure, which you may begin, this procedure you may begin at least with the function itself. So, you may begin with the f. Okay, maybe not. But anyway, it's repeating a procedure or a process, and this procedure never changes. So first of all, it is a loop or repetition. It is a repeated repetition, a loop. Okay, so it is a loop. It is a loop because you have to do this many times. However, how many times you do it depends on the given list length. Okay, so it's a, maybe you might say indefinite loop or a while loop, or in programming languages you might call it can be done as a for loop as well. So in procedural languages or imperative languages, you just assign you just loop through the list, and each time you assign a variable to be the value of a function applied to that, and you assign that to a variable, and this variable is the result. Then you take the next element, then you just apply the result as a function to that element. So definitely you can do this as a loop in a procedural way. So there are a few questions. So how do you do this functionally? Of course, we can do it this way. This is one functional way to do it without assignment. Because you replace this form into that form and repeat until the result remains the same. So this is a functional way to express this, that, which can also be done by assigning them to a variable. So you can do it procedurally or imperatively, or you can do it functionally. But now what is this? What is this thing? I mean, what is this? How does it relate to recursion or I don't know. So, but anyway, that is this is the thing we want. It works. Now all we have to do is just to make sure, each of these F1, F2, those 1, 2, 3, 4 are directory names in a full path. Those are components of the full path. So each F1 will return a association. Then you take the F2, 2 is another directory name, you'll return association. And until you reach F5, then the last one, if it doesn't exist, you create it. You have to say equals to, either a file or like we did here. This part, depending on it's a file or not a file. If it's not a file, we create a container association. If it's a file, we just set it to the file size. Okay, so we can modify this and move on. Modify this so that it actually works. So what we really want to do is originally here, we are given a list of directory names like that, a list of directory path, full path, represented as a list of each directory names. So given a full path, a list of them, we map a function to that list. To this function, we will create a nested association, key value pairs, a tree. So we build a tree. But right now we are at the problem of writing this part, this function. So this can, we know how to do it now, but right now I'm stuck with the logical issues of this. I think that's it for today. Okay. Maybe continue in an hour, I don't know. So, but that's it. Okay, thank you guys for watching. Yeah, because I want to, normally, you should just move on. I should just move on, but it's very interesting. I need a break. Okay, bye guys.